Testing. Okay. I got a grade and then it disappeared. I don't know why. It came out again. Mine's still sign showing. Mine still isn't showing. Okay. Go on and take a look at that. Okay, let's see what's going on here. Oh yeah, I don't know why that didn't. I'm just gonna override it, Sierra. I don't know why it did that. So your current grade is posted. Should be posted. I just posted it. That's kind of weird. Yeah, sounds good. Christian and William, I still have to update yours because of the issues that you're having with the WebAssign. So Sierra, I had to update yours too. I didn't put in a final grade because I had to update yours. So William and Christian, your grade's not going to go lower. It'll go higher if anything. So let me put that in right now, actually, so I don't forget. Okay, William. Okay. Okay. 4, 7.5. And then Christian. That I don't know what the heck is going on with that guy. Okay, and then Christian was the last one that had issues. Oh, maybe he dropped. I don't see a Christian in this class anymore. That's what happens. We get some drops after the first go around. Mine is saying extension is required. Extension is required for what? To see your grade? On Canvas for Chapter 6 test. Well, why are you? Yeah, it's because you never set up Proctorio. The grade is already an average between your work and WebAssign. It's already an average. Okay. So these are your preliminary grades. Okay. Now I have to go through with a fine-tooth comb over the next week and look at your grades, but what I did was I just split the difference. Okay. For your work that you submitted, I downloaded everybody's, I'll show you, I downloaded everybody's exams and I went through them. So I don't know if you guys can see this or not. Oops, can't show you that. But you can see I downloaded everybody's work. Okay, and then I just am going through them one by one, and I'm pretty much done with everybody at this point. Okay. Correct. Your homework grade won't be in Canvas until the very end. Okay, and if you ever want to calculate your homework, your total grade in the class, it's just 15, you just add the 15%. Okay, you just multiply 0.15 times whatever your homework grade is in WebAssign. Okay. I mean, I don't know. Maybe I'll if I have time this week, I'll update that, and I don't know. It's just a big hassle. So yeah, you should be able to do it. You should be able to do that calculation. What does that mean? It's graded on a grading scale. No curving. Yes, there is no curving. There's no curving. Well, I mean, there were 300% on the exam. So how do you curve when 3 of your students get 100%? I'm not gonna, you know, toss those 3 people under the bus so you all can beat them up later. But there is no curve. Does that make sense? Okay, you got to come to class with the skills necessary to do this work. You know, summer school is a privilege, not a right. I hope you guys understand that at this point. Why was your grade increased again? Was it increased 2 times? I only increased it once, unless there's some phantom. Because didn't you tell me that you got number 5 correct, but WebAssign scored it wrong? Okay. Click exactly. See that? That is. There's the gun show right there. Okay. Okay, it is. I gotta flex, Darn. Okay. You want to know why I'm flexing today? I'm flexing today because we are going to be covering today and tomorrow the 4 hardest concepts of the entire course. Okay, these are the 4 hardest concepts of the entire course. So you're going to have to take today and tomorrow serious. Okay. Now what I can't do, I can show you exactly how to do these things. I can give you the homework on how to do these things, and I can do my best to explain them. But what I cannot do is I cannot reteach you guys algebra 2 or trigonometry inside this course. If you didn't come here with the prerequisite knowledge to be successful in this course, I cannot do that for you. Does that make sense? Okay, I love you guys all, but I'm not willing to do the work for you. Okay? So yeah, you know, stuff's getting serious. We took our first exam, right? Maybe some people did better than they thought. Maybe some people didn't do as good as they thought. Okay, but you kind of know where you're standing right now. Okay, now over the next week you're going to have to go through hell. Okay, but in the end, I know who's going to be standing and who's not going to be standing. And if it's worth it to you, you're going to be the one standing. Nah, series is easy. Okay, series is easy. All you do is take a derivative. Okay, and in this case, and in this class, series is easy because you're going to have open note, right? So you're going to be like, oh, well, you know, I'm going to use integral test, or I'm going to use limit comparison test, or I'm going to use the nth term test, right? So in a normal Calc 2 class, yeah, that might be the case. It might be the case where you're like, oh, I got to memorize these 10 tests and know exactly where to use them and when not to use them. And yeah, that's chapter 11. That gets a little bit tough. Okay. That's exam 3, by the way. Okay, in this class, exam 3. Next Thursday, I need to let you know this right now. Next Thursday, not tomorrow. Next Thursday, there will be no lecture. Okay, my lecture will be already pre-recorded, and I will upload that to Canvas. I have a prior engagement next Thursday, unfortunately. Okay, but it's chapter 8.1 and 8.2, and once we get out of chapter 7, you can breathe a little bit easier until we hit chapter 11. Okay, so just to let you know, there is no class a week from Thursday. So keep that in mind. So if you make it through chapter 7, you're good. Well, I'm just saying, if you survive chapter 7, you're doing well. Okay, you're doing well. You're treading water very well. Okay, that doesn't mean you can slough off after that, but chapters 8 and 10, in my opinion, are pretty simple. That's why there's no formal exam on chapter 8 and 10. There's just a quiz. Okay. And then we get into series, and then you just say, hey, well, which series am I going to use where? Right, and then we get into Taylor polynomials, and that's just taking a derivative and evaluating at 0. That's not too hard. And then we're done with the course. That's it. Okay, so chapter 7 is the make it or break it chapter for you guys. Just letting you know that right now. Okay, you thought chapter 6 was hard. Woo-wee. Wait until you get to chapter 7 now. Okay? I don't mean to scare you. My intent is not to put the fear of God in you. My intent is to let you know that I've been teaching this stuff a long time, and this is the wall that every Calc 2 student hits. And all of my Calc 3 students will always say, I'll say, which was harder, Calc 2 or Calc 3? And they'll always say Calc 2. Every single one of them. I said, well, which parts were the hardest for you? And they'll say chapter 7 and chapter 11. Like, makes sense. And I'll say, which one was harder? And I said, probably chapter 7. Okay. Okay. Now that I've given Sierra a panic attack, let's move on. Okay, let's get into the material, because we got about 2.5 hours ahead of us digging into this stuff. Okay, so let's get to working. Okay, I'm gonna go to my sharing here. Okay, first thing we need to cover is something called integration by parts. Okay, integration by parts. I'm going to stop my video for a second so that it becomes a little bit faster, my internet. Okay, 7.1, 7.2 notes. Let's get into this. Okay, integration by parts. So what is integration by parts? Well, integration by parts is an integration technique. Okay, it comes to us from the product rule. We're basically trying to undo the product rule through integration. Okay, so 7.1, okay, is integration by parts. Now, again, normally I would not take 7.1 and 7.2 in the same day, and I'm very sorry that you have to take 7.1 and 7.2 all in the same day. Just take a deep breath and strap in, sit down, buckle up, and hold on to your butts. Okay, integration by parts. Okay, so d dx of u of x, v of x. Okay, this is just the product rule, right? So this is going to be u of x, v prime of x, plus derivative of the second times the first times derivative of the second. Okay, however you want to do the order here. I'm doing it in a certain way just to make a point. Okay, plus v of x times u prime of x. Okay, vx times u prime of x. Okay, that's the product rule. Okay, what would happen if I integrated this guy now? What would happen if I integrated this guy? Okay, so let's think about this for a second. I'm going to integrate d dx of u of x, v of x. Okay, that's going to be equal to the integral, okay, the integral of u of x, okay, dv. Okay, this is dv. V prime is dv. Okay, v prime is dv. It's integral with respect to v, right? We don't need to integrate with respect to u. We just need to integrate with respect to v. Okay, because we're just letting u be the kind of a act like a constant term in this one. Okay, plus, okay, v, this is going to be the integral of v of x, okay, du. Okay, just think of it like that. Okay, so what is this going to be? This is going to be u of x, v of x is equal to, okay, the integral of u dv, okay, plus the integral of v du. I'm going to write it like that. And now what I'm going to do is I'm going to take and I'm going to solve for integral u dv. So integral u dv is equal to, okay, u x vx, okay, or what we would call u v. Okay, I'm gonna write this as u v here. I'm just gonna say this is u v. Okay, u times v minus the integral of v du, and this is called integration by parts formula. Okay, this is integration by parts formula. Okay, integration by parts formula. Okay, so we want to find number one here. We want to find the integral of x times the sine of x. Notice that this is like looks like a product rule, but we're integrating, right? So okay, so I want to decide, well, which one's going to be my u and which one's going to be my v, right? Which one's going to be the u and which one's going to be the v? But we don't really ask ourselves that. What we ask ourselves is which one's going to be the u and which one's going to be the dv. Okay, which one's going to be the dv? Okay, and then there's going to be a du here too, right? So what we're really asking ourselves is which one is the u and which one is the dv? Okay, because that's the original one here, right? So this is equal to the integral of u dv, right? So we want to know which one of these needs to be the u and which one of these needs to be the dv. Is it the x that needs to be the u and the sine x to the dv? Or does the sine x need to be the u and the x dx to be the dv? Okay, well there's a excuse me, I might need to get some water. there is a mnemonic device that helps us know which one to take for u. Okay, for u, what's u going to be? And it's called Lie8. Lie8. Okay, and this is in order of importance to take u in. Okay, order of priority. Okay, so the L stands for logarithmic. If you see a logarithmic, make it your u. Okay, the next one is inverse trig. Inverse trig. The I stands for inverse trig. If it's an I, if you've got an inverse trig, make that your u. Okay, the next one is algebraic, or just a polynomial. Okay, algebraic. Okay, if I have a polynomial, make that the u. T stands for trigonometric. Okay, or a trig function, not inverse trig, a trig function. Okay, and then E stands for exponential. Okay, so if you memorize Lie8, you can't go wrong here. It's Lie8. Okay, Lie8. Logarithmic, inverse trig, algebraic, trig, and exponential. So let's go back to our original function. This is x sine x dx, and we want to do integration by parts on this one. So what is going to be my u? What's going to be u in this case? Okay, what's going to be the u? Which one takes priority? Does the algebra?
X.
Yes. Who was that? Who said x?
Me, Fatty.
Fatty. Thank you, Fatty. Okay. Yes. X takes priority. Why does x take priority? Why does x take priority? Okay.
Algebraic.
It's algebraic. Okay. It's algebraic. Thank you. Thank you, Gene. Thank you, Michael. It's algebraic. It takes priority because it's algebraic. And algebraic always takes priority over trig. Okay, Lie8. Lie8. Okay, so the u is going to be equal to the x, and the dv is going to be equal to the sine x dx. Everybody good with that? Okay, because remember, we want the integral of u dv to equal uv minus the integral of v du. Okay, makes sense? So far, so good? That's a u, by the way, not an a. Okay, so let's get the other pieces of the puzzle here. I need a du and I need a v, right? I need a du and I need a v. Okay, so what's the du in this case? What's the derivative of x? Okay, it's 1. So 1 times dx. So this is dx, right? 1 dx. What about v? What's the integral? What's the integral of sine x? What's the integral of sine x? Yeah, that's negative cosine x, right? Negative cosine x. Okay. Exactly. We don't need the plus c right now. Not until the very end, Eliel, but I appreciate you making sure you always have that plus c. Somebody put that on their exam too. It was really funny. They wrote always plus c, always plus c, always plus c. So I forget who did that, but it was kind of cute. Okay. X. So now we're going to write this as the integral of x sine x dx equals, what's u? U is x. What's v? Okay. What's v? Well, v is the negative cosine x. So this is negative x cosine x minus. Don't forget the minus. You're going to have a lot of sign issues here. If you don't keep your signs straight, you have to keep your signs straight on integration by parts. Okay, this is negative x cosine x minus the integral of v. What's v? Negative cosine x. And what's dx? Or sorry, what's du? Du is dx. Okay. Okay, so we have minus x cosine x. We've got a negative times a negative, which is a positive. So it's positive integral of cosine x dx. Okay, well, what's the integral of cosine x? Yeah, isn't that just sine x plus c? That's where you put your plus c, LEL. Okay, Boom, we're done. We've integrated by parts. Our very first integration by parts. We're no longer virgin integrators. Okay, we have been baptized into the fiery depths of integration by parts. Okay, makes sense? So far, so good? Okay, let's try another one here. Let's try another one here. Okay, integrate. Okay, the natural log of x dx. The natural log of x dx. Okay, and you're like, well, dude, where's the u and where's the v? There's, where did they go? Right? Well, we gotta make them up.
Yeah, this v equal 1 in this.
Yeah, and in this case, okay, what is the dv going to be? Well, what's the u and the, we want u dv, right? We want u dv, u equals and dv equals. So what's u going to be in this case?
Natural log of x.
Yeah, it's going to be natural log of x. Now, why natural log of x? Go back to Lie8, right? Go back to Lie8. What always takes prominence? What always takes priority? Logarithmic. Okay, you're not going to be able to you're always going to choose logarithmic for your u. Okay. Nice. So if u is natural log of x, then what's dv? What's the only thing left over for dv? Isn't that just dx? Right? Yeah, good job, guys. Okay, you guys are paying attention. Exactly. It could be 1 dx or just dx, right? Okay, so we're going to want to integrate the dx and we're going to want to differentiate the du. Well, what's the derivative of natural log? Isn't that 1 over x?
1 over x.
Yes, thank you very much. Okay, it is 1 over x. Okay, and then what's the integral of dx? What's the integral of just 1? Okay, yeah, thank you, Gene. Thank you, Ravi. Okay, not the derivative of 1, Achilles, the integral of 1. Okay, it is x. Very good. Okay, it is x. So now let's put all the pieces together. The integral of natural log x equals u times v. Well, what's u times v? Isn't that x natural log x? uv minus v du. Okay, so what's v du here? Well, that's going to be x times 1 over x, and there's a dx here, I'm sorry. Okay, 1 over x dx. Okay, well, what happens to these guys? Don't they cancel out? That's kind of nice, right? And so now let's take the integral of 1. What was the integral of 1 again? Well, it was just x, right? So this is x, natural log x, minus x plus c. And if I really wanted to, I could factor out the x. So we get natural log x minus 1 plus c. Okay. So far, so good? Okay, let's do some more here. Let's keep spicing it up. Okay, let's make it one step more difficult. Okay, that's how we grow, right? What's my workout program? My workout program is to do 45 push-ups every day. That's one of my workout programs. I try to do a push-up for every day that I've been alive. My goal is to do 75 push-ups at 75. Okay, and that's in a row. That's not taking a break. So I do that as well. I do some rock climbing as well. And I do bike riding. And I do sit-ups and pull-ups. I do a lot of pull-ups. I have a lot of upper body strength, which my son doesn't like, because if he ever oversleeps, I can pick his whole body of a 17-year-old, his whole body up out of bed, and then I put him in front of the dishwasher to do the dishes. So that's like, he doesn't like that though. So he kind of gets pissed off when I do that. Okay. Exactly. So, yeah, but he's a good kid. He's a good kid. I have really good kids. I'm super blessed with my children. So, you want to be able to pick up Jamson. Oh, it was Jamson. Jamson's the one that always said always plus C. Thank you so much.
Pause.
I was always plus C. That was you, wasn't it? Okay. Thank you for that.
That's the only way I remember it.
Exactly. That made me smile. You were listening. So, okay. Okay. Okay, let's move on. Let's do number 3 here. Number 3. Integration by parts. Integration by parts. We're working these muscles. Okay? Working the integration by parts muscles. Okay. So t squared, okay, e to the t dt. E to the t dt. Okay, so we're going to integrate this one. What are we going to use for our u? What are we going to use for our u? The t squared or the e to the t? Okay, yeah, the t squared, exactly. The t squared. So that's going to be t squared. What's du? Du is 2t dt. What's dv? That's going to be the rest of this, e to the t dt. And then what's v? Well, that's easy. That's just e to the t, right? Okay, the integral of an exponential is an exponential. Okay, that's kind of cool. Okay, so we're going to get the integral of t squared e to the t is equal to uv. Now what I do when I do this on my paper, this is what I do. I draw a little arrow. Okay, I do this. I go boom, boom. And what that tells me in my mind is to do uv v du. uv v du. I don't care about this guy over here. uv v du. So I'm going to go uv, which is t squared e to the t, minus the integral of v du. Well, what is that? That's 2t e to the t dt. Okay. Well, that's kind of interesting. Except over here, what do we have? Well, we have another integration by parts. This is integration by parts by parts. Okay, now, is this going to end up getting less complicated? Absolutely, it will. Okay, it will get less complicated. Okay, because every time I do integration by parts, what's happening to that power? Isn't it going down by 1 power? Aren't I chopping that polynomial down every single time I integrate by parts? I chop the polynomial down by 1 power, and eventually I'm going to make it a constant, and what's going to happen is here I'm going to make it a constant in my next step. So now we got to do integration by parts again. Oh, okay, just on this piece here. So what's u going to be? Well, let's make it our 2t. Okay, what's du? 2 dt. What's dv? dv is going to be e to the t dt. And then what's v? E to the t. Again, uv v du. Now we got to make sure that we put parentheses here, because otherwise we're going to get some sign issues. Okay, t squared e to the t minus parentheses uv. That's 2t e to the t minus the integral of 2 e to the t v du e to the t dv. No, dt, sorry, dt. Okay, and what did that accomplish? Well, it accomplished us to be able to integrate now. Okay, because the integral now has it only has 1 variable, not 2. Okay, so what is the integral of 2 e to the t? Well, that's 2 e to the t plus c. Okay, so that's a minus there. That's a 2 e to the t, and then we're going to distribute. Okay, we're going to distribute our negative sign. Okay, so distribute the negative sign, and I get this to be t squared e to the t minus 2t e to the t plus 2 e to the t, okay, plus c. Now, the last step that I'm going to do is factor out that common factor of e to the t. And I get e to the t, it's not a very nice t, e to the t is equal to t squared minus 2t plus 2, that's a quadratic, plus c. Okay, and that's it. So what did this equal? This equaled the integral of t squared e to the t dt is equal to this guy. Boom. Nice.
So, Professor, whenever there's another like sort of expression like that, the integral, and there's another like algebraic logarithmic, we would do integration by parts, like until we get rid of
Yes,
each one, or
until you,
Okay.
you keep chopping it down. So, yep, you just keep doing it over and over and over again. Okay. Okay, now sometimes when we chop it down, we don't get anywhere. Okay, we're going to address that in the next one here. Okay, and there's a trick that we can use. Okay, we can use a trick. If you just do, wouldn't the C be negative? Yeah, David, what's a negative of a constant? Isn't that just a constant? Yeah, it's still plus C. It's always plus C. Don't forget, always plus C. Okay, so we don't bring down the original function. What do you mean the original function? Don't bring down the original function. I said this is equal to this. I did bring it down. I don't know what you're talking about. Yeah. Okay. So review the tape. Okay, number 4. Okay, number 4. Evaluate. Okay, evaluate the integral of e to the x sine x dx. Okay, e to the x sine x dx. Okay. Okay. So u is equal to sine x. Okay. Du is equal to what? Well, dv is equal to what? Isn't that e to the x? Okay. Now, right? Does that make sense? Why? Because again, liate, right? Liate, what comes first? Trig over exponential. Does that make sense? Trig over exponential. Okay. Okay. So du, what's the derivative of sine x? Wasn't that cosine x? X. What's the integral of dv e to the x? Wasn't that just e to the x? Now the problem with this is what's going to happen is we're going to oscillate back and forth forever. Okay, we're going to oscillate back and forth forever, but that's okay because eventually we're going to get back to where we started, and that's going to help us. Okay. Yeah, thank you, Susan. Yeah, I don't know why some people don't teach that. I don't get it. So yeah, but thank you. Okay, I just don't. Yeah, it is. It's extremely helpful. Okay, so now it's just a claim to. I'm glad that I know it because then I can explain it really well. Okay, so now what are we doing? Okay, evaluate. Okay, this guy here. Now, again, we're just going to keep going back and forth, back and forth, back and forth. We're going to keep doing integration by parts, but we're eventually going to get back to where we started. Okay, we're going to get back to this guy here, and that's going to be extremely helpful for us. So let's go ahead and do this. Okay, so we have the integral of e to the x sine x dx is equal to, okay, e to the x sine x is equal to uv. Well, that's e to the x sine x, right? E to the x sine x, yep, minus the integral of e to the x cosine x, e to the x cosine x. Okay, that's kind of cool. Okay, and there's the dx here. Okay, so now we're gonna have to do integration by parts again. This is e to the x sine x minus, okay, well, what's u? U is equal to cosine x. What's v, or what's dv? dv is equal to e to the x dx. Okay, what's v? V is equal to e to the x. What's du? du is equal to negative sine x dx. Maybe I can squeeze the dx in there. Okay, let me move the dv over. Okay, and so we're going to say, I'm going to move this down. This is going to be equal to now e to the x sine x minus, okay, minus what? Well, what's u? This is going to be e to the x cosine x. So e to the x cosine x minus the integral of negative e to the x sine x dx. Okay. Okay. So now I'm done. I'm good. I'm absolutely good on this one. I can easily solve. Why? Well, let's distribute the negative sign and see why we're done. We have e to the x sine x minus e to the x cosine x plus the integral of e to the x sine x dx. And didn't we just end up where we started? Right? Didn't we just end up where we started? Is this a negative? This should be a negative, right? Did I mess up? This is plus. I messed up on a sign here. There's 3 negatives here. 1, 2, 3. Yeah, this is a minus. Okay, I want it to be a minus. Okay. Okay, thank you. Okay, so now we've got e to the sine x minus e to the cosine x minus the original thing that we started with. Well, I'm going to do some algebraic manipulation here, and I'm just going to add what we started with. E to the x sine x dx. I'm going to add that to both sides. E to the x sine x dx. Okay, so what does that give me? That gives me 2 integral e to the x sine x dx is equal to e to the x sine x minus e to the x cosine x all over 2. Boom. Plus c. Always plus c. And we're done. That's it. We're done. We did it. Okay. There's a little algebraic trick there. And that's the integral. That's the integration by parts. Okay. Okay, let's talk about what happens when we have to do a definite integral with this. Okay, a definite integral. Okay. I'll leave that up there for those of you a little slower at copying. Okay, so a to b of u dv is equal to uv evaluated from a to b, okay, minus the integral a to b of v du. We're just going to do integration by parts, but we have to evaluate this first guy with respect to b and a. Okay, so that's the only difference. Okay, with integration by parts. Okay, for definite integral. Okay, so let's do number 5 here. Let's do number 5. Number 5 says, okay, 0 to 1. Okay, 0 to 1. Okay, of the inverse tangent of x dx. Okay, the inverse tangent of x dx. Okay, well, what's the integral? Well, I mean, what are we going to do?
I'm sorry for cutting you off. I didn't get number 4. I didn't get what happened. Like where did we get like, oh, I don't get it. Yeah, like, yeah, because what happened here with the integration of e to the x sine dx.
Right.
Yeah.
Okay, so what I did was
So you added.
Yeah, I remember, you know how we got the exact same thing? Think of this as like d, right?
Mm-hmm.
D. And what did we start with? We started with d. So what happens when I add d? This is a minus d, right? So what happens if I add d to both sides? Wouldn't I get 2d? Right? So add a d with a d. Wouldn't you get 2d? Right? Does that make sense? I'm saying this, the integral is equal to this thing plus or minus the original integral. And so all I did was add the original integral to both sides to get double the integral. Double the integral is going to equal e to the x sine x minus e to the x cosine x. This is double the integral, the original integral. e to the x sine x. And so all I have to do is divide by 2 and put a plus c.
All right, thank you.
You're welcome. Okay, so now let's do integration by parts on this thing. Okay, and see what we get. Okay, see what we get here. Okay, so okay, now keep in mind that the integral of the inverse tangent of x, okay, is not 1 over x 1 plus x squared. The integral of this is inverse tangent of x. So don't think backwards on this one. Okay, the integral of that is inverse tangent, but the integral of inverse tangent is much more complicated. Does that make sense? Don't think, oh yeah, this is just 1 over 1 plus x squared, because it's not. The derivative, okay, the derivative of inverse tangent is 1 over 1 plus x squared. So don't get the integrals and derivatives confused. Okay? Does that make sense? Just don't do that. Okay, it's bad for your health. It's bad for my mental health. Okay. So the inverse tangent of x. Okay, so how are we going to do this? Well, we're actually going to do a trick. We're going to use integration by parts to help us solve this. We're gonna set up a UDV. Okay, set up a UDV. Now I'm only teaching you one way to do integration by parts, but I'm just teaching you my way because I like my way, and I'm the teacher, and so you're going to learn the way I like. So there you go. Okay. Okay. If you want to learn another way, go take another class. Okay. Go watch a YouTube video. There's tons of them out there. Okay. Okay. So you what? Let's go back to Lie8. Okay, what are we going to use for our u? What are we going to use for our u? Well, what do we have? We have an inverse trig function, don't we? We have an inverse trig function, okay? Inverse trig function, okay, for our u, okay? And then for our dv, I'm just going to use dx, okay? So u is our inverse trig function. We're going to use that, okay? Sorry, you know what? I wrote this wrong. I don't know what the hell's wrong with me. Okay, Lie8. Okay, we're going to do inverse trig before we do algebraic. That's the idea here. Where inverse trig is the inverse tangent. Like, there's a reason it wasn't making sense. And the algebraic is 1. Okay, is 1. It's 1 times inverse tangent. So what we want to do is we want to take the derivative of this thing instead of taking the integral. And what the tool that's going to allow us to do that is integration by parts. We're going to make this thing the inverse tangent, turn that into a derivative instead of an integral. Okay? And so this is v is equal to x. And this guy here, du, is equal to 1 over 1 plus x squared x. Okay? You following me so far? Hopefully. Okay, hopefully. You feel me? Okay, school's in session. Someone's going to be taught a lesson. That's all I have to say. Okay. Anybody decide to change their major yet? I'm just joking. All right, that was a joke. That was a joke, people. Lighten up. Sierra, lighten up. Okay. Has anybody changed their major at this point in their life? At least once? Has anybody been like, yeah? Sierra's got the unsmiley face there. Okay. I'm just playing with you, Sierra. You're doing okay. Okay. I thought about it a lot. Victor says he thought about it a lot. Okay. Can I let you know that I had to change my major in college? I had to change it once, right? So again, going back to my high school, I hated everybody in 9th grade. It was a really bad year for me. I hated everybody. I wanted everybody to die. It was just a bad year. But then I went away to it was really bad. It was serious. This was some serious stuff, man. I did not grow up in a really good environment. I actually grew up in a really bad environment, probably one of the worst that you could ever imagine. And I'm not going to go into any details on that, but it was extremely awful. Okay. I grew up seeing things that kids should just not see. Okay. I did not grow up in an extremely nice family with nice parents. Okay. So in ninth grade, I just hated everybody. Okay. I came home one day to my family and I looked at them straight in the face and said, you guys are all screwed up and I want nothing to do with you. And that did not go over too well. I'll tell you that right now. Okay. But at 13 years old, I knew that I was destined for something better than the crap that they had given me up to that point in my life. And so I turned to my mom, I turned to my stepdad, and I turned to my sister and just said, you guys are all effed up and I don't want anything to do with you guys anymore. And so that's why I was pissed. I was pissed at everyone. I went to my school counselor. I know, right? Exactly. So I have 5 kids. That's a different part of the story. But yeah. No, I have 3 stepkids. I married into 3, and I have 2 of my own. Okay. Exactly. That's my claim to fame. So anyway, so in 9th grade, I hated everybody. Everybody I hated. I went to school, I did my work, I came home and I played Sonic the Hedgehog, and that was my life for a year. I read Sherlock Holmes and played Sonic Hedgehog for an entire year, and I was done with everybody, and I had no friends and I had no life, and I was over. I was done. I was like, I hate my family. They're all worthless, and I was not happy at all. Well, a counselor at my high school, she saw that, I was at risk. And I'm like, what are you talking about? I'm at risk. She's like, yeah, you're at risk youth. I'm like, I'm scoring A's and I got A's in middle school. What do you mean I'm at risk? She's like, yeah, you're at risk. And I'm like, oh, okay. And so she suggested that I go away to a camp and get out of my environment and go away to this camp over summer. And it changed my life. So that camp, I decided as a sophomore in high school, I decided that I wasn't gonna deal with the shitty hand that was dealt me, and I was gonna actually make something of my life. And that year, I started pulling straight A's. I started pulling straight A's that year, and then I pulled straight A's the next year, and the next year, and the next year, and just kept doing it over and over and over again. Education was my out. It was my out of this ghetto life that I was in. And so I went to college, right? I graduated from high school with honors, and they gave me this yellow sash, CSF, California Scholarship Federation Association, and I had the golden seal of recognition from the state of California that I was awesome, because I didn't want anything to do with the drugs and the alcohol and all the sex and all the perversion from my family of origin. I was out of there. I was done. I hadn't wanted nothing to do with those people. And so I went off to college, and I couldn't afford to go off to a 4-year university. I had to go off to a 2-year university. One of the reasons was because my sister had gone off to college 3 years earlier, and she needed all the money. She got a ride to Pepperdine University in economics, in business econ, and but it was a really expensive college. It was one of the most expensive ones on the state of California, other than Stanford. And so my parents basically came to me and said, Jason, there is no money for you to go to send you to college. You're going to have to go to a 2-year college. I said, oh, that's wonderful. Thank you so much. Thank you for nothing again. And so I was a little more mature at that point. I didn't say thank you for nothing. I was just like, yeah, okay, well, I hope Jennifer does well with her career and makes a lot of money and she can support me. No, I'm just kidding. So my freshman year, I decided, okay, you know what? I'm smart and I know science and I know math. And so guess what I'm going to do? Anybody have any idea what I decided to do as an 18-year-old punk with my life? I'm good in science, I'm good in math, and I want to make money. Okay, Frederick says engineer. Very close, very close. Okay, but engineers don't make the top billing. They don't make the ching ching. What makes the ching ching? Exactly. Eliel got it right on the head, nailed it right on the head. I was like, oh, I'm going to be a doctor. Right? I'm like, hey, I'm good in math, I'm good in science, I have a strong work ethic because I learned from the mistakes of my parents. And these people, you know, I don't want to be anything like them. And so I was like, I'm going to be a doctor. I'm going to be a doctor. So I was living at home, and I was driving home from my community college at the time. It was Moore Park College up in Ventura County. So I was driving home from community college. I was taking my biology class and taking my calculus class. I was a freshman in college, and I walk in the front door. Now we had tile in our front door of our house, and it was white tile. And I saw a trail of blood from the kitchen all the way to the bathroom. And I'm walking in, I'm thinking, okay, who died? Right? Who just got shot? Right? And so, yeah, so a trail of blood all the way from the dishwasher all the way into the downstairs bathroom, and there's this trail of blood along the tile. Well, I take 2 steps forward into that house and I faint dead out. Boom. Flat out. And the next thing I know is I see my mom like patting me on the face. You got to see this. She's like patting me on the face. She's like, wake up. She says, Jason. I'm like, yeah, Ma? And she says, do me one favor. I said, yeah, Ma, what do you want me to do? She says, change your major. Exactly. She says, you're not going to be a doctor if you're fainting at blood. What happened was she nicked her Achilles tendon on the dishwasher, and it created a little faint trail of blood all the way to the bathroom where she was trying to clean herself up. And she said, you're not going to be a doctor if you can't handle the sight of blood. You fainted dead over. Boom. Right? And I was like, yeah, I think you're right. But I think at the same time, I was taking biology, and I just didn't have any passion for biology. I was taking biology and I was taking calculus at the same time. I loved calculus. I fell in love with calculus. Okay. Yeah. Exactly. So I fell in love with calculus. I fell out of love with biology, and I was like, okay, I'm gonna devote myself to mathematics, and that's exactly what I did. So anyway, that's my story about changing your major. Okay, it's okay to change your major. Okay, not everybody's designed to do the exact same thing. If we were, it'd be an extremely boring world, and there's a lot of jobs that would not get done. So just keep that in mind. Okay, let's go back to Lyate here. Okay, number 5. We're doing our integration by parts. So let's speed through this thing. Okay, we're almost halfway done, which is good. Okay, so we're going to do integral from 0 to 1 of the inverse tangent of x dx, okay, is equal to, okay, x times the inverse tangent of 1 of x evaluated from 0 to 1 minus the integral of 0 to 1 of x, this is v du, right? uv v du. So x over 1 plus x squared. Oh, okay, dx. Okay, so now I can evaluate this guy here, right? Or maybe I'll just leave him like that for right now. I'll leave him like that for right now. We'll evaluate in the next step. But I want to integrate this guy here. How am I going to integrate this guy here? Well, that's just a regular u sub. Why is it a u sub? Because the derivative of 1 plus x squared is 2x. And that's going to give you my du. So this is a regular u sub. U is equal to 1 plus x squared. Du is equal to 2x dx. and then divide by 2, we get du over 2 is equal to x dx. Okay. Okay, so this is going to become, okay, this is going to become x times the inverse tangent of x from 0 to 1, okay, of negative, okay, of, okay, the integral of 1 to 2. Now, why 1 to 2? No, there isn't, unfortunately. Okay, 1 to 2. Okay, yeah, because when I plug in 1, okay, when I plug in 1 here, it's 1 plus 1 squared, which is 2. It's the u. We're just changing our limits of integration. Okay, so I don't have to change back to x at the very end. So now what's this going to become? Well, this is going to become 1 over u. This is 1 over u, du over 2. Okay. Right? So this is going to become x inverse tangent of x from 0 to 1 minus, now let's integrate this. This is going to be natural log. This is 1/2 natural log of u evaluated from 1 to 2. 1 to 2, okay. Cool. Now let's just plug in our limits of integration here and evaluate. So I'm going to plug in 1. This is 1 times the inverse tangent of 1 minus 0 times the inverse tangent of 0 minus 1/2, I'm going to put this in parentheses, minus 1/2 natural log of 2 minus 1/2 of natural log of 1. Okay. Well, this thing goes to 0, and so does this. That goes to 0, and so does that. Okay. What's the inverse tangent of 1? What's the angle whose tangent is 1? Yes, thank you, Susan. Pi over 4. Okay, pi over 4. Does that make sense? It's the angle whose tangent is 1. Okay, it's pi over 4. Okay, and then minus the 1/2 natural log of 2. And I'm just going to rewrite this guy, this bad boy over here. Okay. Okay, and this is natural log of radical 2. Okay. Does that make sense? Is that good? I mean, that is some good mathematics right there. That is some sexy math. I'm just letting you know right now, okay? That is some nice stuff right there. Okay. Plus,
Professor, you forgot the C.
Did I forget the plus C?
Yeah.
I did?
It's a definite.
Really? It's a definite integral. Exactly. Okay, these are numbers, people. There you go. So, know your definites from your indefinite. Okay, exactly. You're welcome. I don't mean to make fun of you. I do, but I mean, I hope you don't take it personally. Okay. You can beat me up later. It's all good. Oh, absolutely, Sierra. The best way to do this is to do it over and over and over and over again. That is how you get good at integration by parts. Over and 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 over. Over forever. Over forever. Exactly. Grind. You grind through this. You just do problem after problem after problem after problem after problem after problem. How do you think I got good at it? Right? That's how I got good. Because I'm like, okay, this one works like this. This one works like this. This one works like this. This one is just over and over and over again. You hit the nail right on the head. Okay, it seems relatively simple. I'm glad you think it seems relatively simple. Thank you. Good, Victor. Okay. It's not really relatively simple. Could you go over a hard problem? Absolutely. Let's go over a hard problem here. Let's derive a formula for Victor. Okay, let's do a proof, a formal proof of an identity in integral calculus just for Victor. Okay, you ready? You ready, Freddie? Or Fady? Or Fadi? Or Fatty?
Whatever. Yeah,
I think I got it right on the last one, right? Fatty?
fatty. Yeah.
Yeah, okay. Okay, so is there a Freddie in here too? I think there's a Freddie in here too. I think so. There's a Fatty and a Freddie, I think. Okay, so let's do number 6 here. We're having so much fun with integration by parts. Let's step it up a notch, shall we? Let's put our big boy pants on, and let's do an integral that's fun. This is going to be fun. Okay, this is fun stuff. Okay, show, and I need to slow down on this one, otherwise I'm going to make a ton of mistakes. Okay, and I don't want to make any mistakes. Okay, this is a no mistakes problem. Okay, so sine, show that the integral of the sine of n of x dx is equal to negative 1 over n times the cosine of x sine of n minus 1, n minus 1, okay, n minus 1, x plus n minus 1 over n times the integral of the sine of n minus 2, n minus 2 of n of x dx. Okay, I want to show that no matter what the power of sine is, when I integrate, I can always plug it into this formula. Okay, and just keep getting a recursive formula over and over and over again. Okay, let me make sure that that's written correctly. Minus 2. Okay, so let's do integration by parts here, right? Integration by parts. Okay, so u is equal to what? For the sine, okay, the sine function. Well, I don't have 2 functions here, so I have to make 2 functions out of 1. So here's what I'm going to do. I'm going to do something sneaky. I'm going to do the the integral of sine to the nth power of x is equal to the integral of sine to the n minus 1 power of x times the sine of x. You guys okay with that? You see, all I did was break off a sign. Okay. Is that good? Okay. It looks simple. David says it looks simple. Okay. Yeah, let's see. We'll see how simple it is. Okay. So I broke off a sine x. Okay. So now what I'm going to do is I'm going to do integration by parts. The problem comes in which trig function do I want to integrate and which trig function do I want to differentiate? Okay. Well, differentiating is a whole lot easier than integrating, in my opinion. So I'm going to use the more complicated one to differentiate. So I'm going to say u is equal to sine to the n minus 1 power x, and dv is equal to sine x dx. Okay? So we're going to do v is equal to, negative cosine x, and du is equal to what? Well, this is going to be, bring this guy down, right? This is going to be n minus 1 times the sine of n minus 2 of x times cosine x, right? dx. Okay, that's the chain rule right there. Does that make sense? Okay, chain rule. Okay. So now we're going to go uv vdu, right? uv vdu. Okay, so this is going to be equal to negative sine negative n minus 1 negative sine to the n minus 1 power of x times the cosine of x minus the integral of n minus 1 times the sine of n minus 2 x times the cosine, okay, this is going to be negative cosine, well, it's time cosine x times negative cosine x. And that's a dx. Let me put some parentheses here so I don't get confused. Okay. So far, so good? Okay, so far, so good. Okay, so this is going to be equal to negative sine to the n minus 1 of x cosine x. I'm going to pull that negative out in front and make this positive. So this is the integral of cosine squared x times n minus 1. Well, let me do it like this. This is going to be n minus 1 times the sine of n minus 2 to the x times cosine squared x dx. Okay. Okay. Let me write this n minus 1. Now, what I'd really like to get this is in terms of sine. Well, how am I going to get this in terms of sine? Let's change the cosine squared into 1 minus sine squared. Let's change the cosine squared into 1 minus sine squared. Let's rewrite this. This is negative sine of n minus 1 x cosine x plus the integral of n minus 1 times the sine of n minus 2 x times 1 minus sine squared x dx. Now let's distribute this. Okay, let's distribute. So this equals, okay, this equals the negative sine n minus 1 of x cosine x plus, okay, let's distribute this thing. This is going to become the integral of n minus 1 times the sine of n minus 2 of x, okay, minus n minus 1 times the sine of n of x dx. Oh, isn't that nice? Okay. So now I'm going to break this up into two different integrals. Okay, break this up into two different. This is negative sine to the n minus 1 of x. Okay, cosine x plus, okay, this is integral of n minus 1 to the sine of the n minus 2, okay, times sine of n minus 2 of x, minus the integral of n minus 1, okay, n minus 1 of sine of nx dx. Okay, and what did this equal? This equaled my original integral of sine of n of x dx, right? Didn't that equal my original integration? Does that make sense? Okay. Great. So what do you think I'm going to do now? Any ideas? We've got the same thing over here as we have over here. So what do you think the trick is that we're going to do? Yep, we're going to add, exactly, Sierra. We're going to add integral of n minus 1 of sine n to the x dx to both sides. We're going to add n minus 1 times the sine. Okay. Now what is n? N is just a constant. Does that make sense? N is just a constant. So I could really pull this n minus 1 out in front, couldn't I? And I would get n minus 1 times the integral of sine of n of x dx is equal to this whole thing. Okay, this thing here, I'll put this in parentheses or in quotes. Okay, and so what happens over here? This cancels. And then what does this become? Well, isn't this just 1 sine nx? So what happens when I add n minus 1 plus 1? N minus 1 plus 1 becomes n. Oh, okay, that's kind of cool. So this is n times the integral of sine to the nx dx is equal to, oh, look at that. We have something that has an integral that we want to solve for equals something on the other side. Oh, okay. So this is going to be negative sine n minus 1 of x cosine x, right? Plus, what do we have here? The integral, okay, oh, there's a dx here. I left off a dx, I'm sorry. Okay, I was neglectful. There we go. The integral of n minus 1, okay, times sine to the n minus 2 of x dx. Okay, Cool. Getting there. Okay. What else we got here going on? Okay, well, how can I solve for my original integration? Well, let's divide by n. Let's divide everything through by n. Okay. So then this becomes the integral of the sine of nx dx is equal to negative 1 over n times the sine to the n minus 1 of x cosine x. Okay, I can pull the n minus 1 out in front, and that becomes n minus 1 over n, this is plus, times the sine, integral of the sine of n minus 2x dx, and that's exactly what we wanted. There is our integration formula. And you will actually find this integration formula in the back of your book in the table of integrals. So what we just did was we just took and used integration by parts to derive a very, very complicated integration formula. Okay, is that good? Is that all good? It's all good in the hood? Okay.
Professor, how can we have added like the n minus 1 over there with a sine n to the x, like here on top, yeah. So we added the integration of sine n.
N is just a constant. N is just a power, and everything we know about powers is that they're integers. Okay, well, they don't have to be integers, but for the most case, they're integers. So they're just numbers. They're just real numbers. Okay, there's no imaginary. There's nothing about n that's weird. So we can just add the n's. Okay, we can add, subtract, and multiply and divide by n. Okay, because if n was 0, okay, so this was a proof. Yeah, every problem like this is a proof. Okay, if you want to put a little QED here, you can put a little QED. That is a proof. Even when you did your trig identities in trigonometry, you were doing proofs. You just didn't know it. This is called an algebraic proof. This is an algebraic proof. Okay, does that make sense, Sierra? You proved that the right side is equal to the left side and that those will be true forever until the end of time. Okay, so yeah, this was a proof. Okay, it was a problem proof. Okay, every problem is a proof. Okay, we just don't formally think about it that way. Okay, so this leads us into 7.2. So 7.2 is trigonometric integrals. Trigonometric integration. Okay, trig integrals. Okay, how are we going to deal with some trig integrals? Okay, well, we got some rules to go over here. Okay. Okay, so for the integral of sine to the m x cosine one second. Cosine to the nx, m comes before n, right? In the alphabet, I think. Okay, nx. Okay. So how do we deal with integration by this? Well, we have some rules. We have some rules of approach on this one. Okay, for something that looks like this, we have it's a 4-step process. Okay, four rules. Okay, number 1. Okay, let me make this a little bit bigger. Number 1, if, okay, the power of cosine okay, is odd, okay, save one cosine factor, okay, and use, okay, 1 minus sine squared x for remaining cosines. Use 1 minus sine squared x for the remaining cosine. So if cosine is odd, we can break off the odd and make cosine even. Does that make sense? And so once we make cosine even, we can use the Pythagorean identity. 1 minus sine squared x for the remaining cosines. Okay, for their cosines. That's the first rule. 2. If the power of sine is odd, okay, if the power of sine is odd, save one sine factor. Okay, so save one sine factor and use 1 minus cosine squared. This is the same thing. And use 1 minus cosine squared x for remaining sines. So same trick, just okay, same trick. Okay, just a flip side. Number 3, if the power of the sine and cosine are both odd, then either 1 or 2 can be used. Either 1 and 2. Okay, if both odd, use it's up to your discrepancy, whatever you want to use. Use 1 or 2. Okay. 4. If both are even, then use a half angle identity. Now, you're going to need to know this half angle identity. I don't know if I've talked about this already, but you're going to need to know this half angle identity by heart. We're going to be using this from here until the end of the entire course. Okay, so if both are even, then use a half angle identity. Okay, then use I'm going to put the half angle identities. Okay, I mean, I guess since this is open note, you don't really need to memorize anything, but it would be good to have this memorized because you're going to run into it a ton. Okay, if both are even, then use the half angle identities. Sine squared x is equal to 1/2 times 1 minus cosine 2x. Okay, cosine squared x is equal to 1/2 times 1 plus cosine 2x. And sine of 2x is equal to 2 times sine x cosine x. Okay, so there's a bunch of half angle identities, double angle identity and half angle identity. Okay. Okay, so we're going to use these trig identities to evaluate if they're both even. Okay, that's the hardest one, is when they're both even. But it comes up a lot, especially in Calc 3. We use it a ton in Calc 3 too. So if you could memorize it now, you're going to save yourself a lot of headache in the rest of this course and in Calc 3. A ton. We use it a ton in Calc 3. Okay, so number one, evaluate the integral of the cosine cubed x dx. Okay, so what are we going to do here? What are we going to do here? Cosine is odd, so what are we going to do? What's our first step? Any ideas? Survey says factor, save a cosine. Yeah, break off a cosine, right? We're going to break off a cosine. Okay, we're going to break off a cosine. So we're going to go cosine squared x times cosine x dx. We're going to save a cosine at the very end. Very good. Okay, and then what are we going to do? We're going to change the cosine squared into sines. So this is 1 minus sine squared x times cosine x, right, dx. Okay, so now what are we going to do? Well, I'm going to distribute the cosine x. This gives me the integral of cosine x minus sine squared x cosine x dx. Now what I'm going to do is I'm going to break this up into two integrals. This is the integral of cosine x dx minus the integral of sine squared x cosine x dx. Okay, what's the integral of cosine x? Not everybody at once. Okay, I don't want you talking over each other. Okay, the integral of cosine x is not negative sine x. It's sine x. It's just sine x. Very good. Sine x. Thank you for playing. We have lovely parting gifts. I think we have some rice-a-roni, the San Francisco treat. Okay, so yes. Oof. Don't. You could be like Homer Simpson. Don't. Okay, sine x minus, okay, what? minus what? This is a u sub, right? Isn't this a u sub? U is going to be equal to sine x. What's du? Du is equal to cosine x dx. Oh, that's kind of cool. Okay. Oh, is the audio glitching? Okay, let me fix that. Testing, 1, 2, testing, testing. There we go. Is that better? Better. Okay, thank you. Okay, yeah, just let me know if the audio or video ever goes out. I can try to make it better. Okay, so this is u du. This is just a regular u du. No integration by parts necessary here. Okay, no integration by parts necessary, just a u du. Okay, u do u. Okay, u do u. Okay. So now what we're going to get is we're going to get the integral of u squared du. Well, that's kind of cool. Sine x minus the integral of u squared du, right? Okay. Well, what's the integral of u squared? Isn't that just u cubed over 3 plus c? Don't forget your plus c. And then what was u? What was u? Wasn't u sine x? So isn't this just sine x minus 1/3 sine cubed x plus c? Boom, done. That was easy. Easy peasy lemon squeezy. Okay. Okay, let me get my easy button because I don't like saying it.
That was easy.
I like him saying it. What was that?
That was easy.
Exactly. That was easy. Okay. I don't even know why I have to teach you guys. I don't even know why you guys need me. You guys are that smart. Okay. All right. Okay. Number two. Okay, let's try this one. This one's fun. This one is really fun. Okay. The next two, super fun. Super fun. Super friends. Okay. I think I'm getting a little punchy. That's okay. Okay. Let's find the integral. I kind of yelled at a kid this morning, so that was kind of like, yeah. So, but he was being a moron, so it was okay. So, I'm like, I asked him many times to put a shirt on if he was going to show his video, and he refused, and so I had to kick him out of class. And I'm like, dude, if you're going to be on camera, wear some clothes. And he didn't understand that. So I had to get all in his face and be like, do you understand that this is college? I think that this might have been like his first college class. I don't know. I don't know what's going through these kids' heads these days. I do. I kind of do, because I have a high school senior that I live with on a daily basis. But anyway, but him, I can pick him up and throw him in front of the dishwasher. My students, I can't do that. I would get arrested for that. So, exactly. I can't be like, here, put this shirt on now. Put it on now, or get out of my class. This is not high school. I don't understand why these people think it's still high school. It's high school mentality. It's like, step it up a notch, okay? Show me some respect. Don't be disrespecting my classroom by coming in with your nipples all showing. That's disgusting. Get these people. Hide those nips. What is wrong with you?
That was easy.
Exactly. That was easy. Okay, let's get back to work. I digress. I apologize. Okay, so integral of sine of 5x. I don't mean to offend anybody in here. If I offend you, please let me know. I not mean to offend you. Okay, so, and if you are a minor, just close your ears, okay, when I talk. Let's just sorry. I get a little over the top sometimes, but the guy really pissed me off. See, this is free therapy for me, and you guys get to pay. So it's really just a win-win for me. It's really a win for me. So there you go. Okay, I get to vent to you guys, and it's all good, except we got to be doing calculus. So let's go back to the calculus. Okay, let's go back to the good stuff. Okay, sine of 5. Sometimes I crack myself up. It's really stupid, though. Okay. Anyway, sine to the whatever. Sine to the 5th power times cosine squared. What are we going to do? We have one that's odd and one that's even, right? We have one that's odd and one that's even. Well, let's break off the one that's odd. Let's do the exact same thing we did before, but instead of with a cosine, right? Instead of breaking off a cosine, we want to break off a sine, right? So let's do that. Let's break off a sine. Let's go sine to the 4th power of x times the cosine squared x times a sine x dx. Okay. Now I want to change the sines into cosines, okay, if I can. So this is going to be 1 minus cosine squared x squared, right? Because isn't that sine squared squared, sine squared squared? Does that make sense? I don't want to lose anybody on this step. But it's sine to the 4th is sine squared squared, right? Well, what's sine squared? Sine squared is 1 minus cosine squared. Okay, that's good. Times cosine squared x times sine x dx. Okay, well, that's kind of cool. Okay, so now I'm going to distribute the. Well, I'm gonna multiply this out. Actually, I'm going to go 1 minus 2 cosine squared x plus cosine to the 4th x times cosine x, cosine squared x, times sine x dx. Okay, well, that's kind of cool. Now I'm going to distribute the cosine x, and I get cosine squared x minus 2 cosine to the 4th x plus cosine to the 6th x, all times sine x dx. Okay, so now what I'm going to do, I'm going to do a u sub on this thing. Okay, u is equal to cosine x. Well, what's du? Negative sine x dx. Okay, so now what I'm going to do, did my screen freeze? Dang it. I hope my screen didn't freeze. Come back to me. Come back to me. Yes, of course it did. Come back, little boy. Start the CPR. Come back. I can't lose you. Okay, you complete me. There we go. We got it back. Whew. That was good. That was a close one. Okay, that was a close one. There's a bunch of whiners in this class, so it was close. I was going to have to call the wambulance. So anyway, forget that. That's what you call on the whiners. You call the wambulance. Okay. Thanks. Okay. So we have our u, right? Our u is our cosine. So let's just plug this in. U squared, right? U squared minus 2u to the 4th plus u to the 6th times negative du, right? Times negative du. I'm going to put the negative in front. Negative du. Okay. I'm going to pull the negative all the way out in front if that's okay with you. Okay. So let's do negative of the integral of u squared minus 2u to the 4th. That's a 4. Okay, plus u to the 6th. Okay, du. Okay, so this is just going to be u cubed over 3 minus, this is going to be 2/5 u to the 5th plus 1/7 u to the 7th. Okay, that's all with a negative on front and then a plus c. And then I want to know, well, what was u? U was cosine, right? Wasn't it cosine x? So this is going to be negative 1/3 cosine cubed x plus 2/5 cosine to the 5th x minus 1/7 cosine to the 7th x plus c. Okay. Okay, let's try number 3 here. Number 3 is the integral from 6 to pi of sine squared x. Sine squared x dx. Okay, sine squared x dx. Okay, so what are we going to do here? Well, this is an even one, right? So we got to use one of those half angle identities. So sine, I always think sine as negative and cosine as positive when I'm dealing with half angles, okay? Cosine is plus cosine, and sine is minus cosine, okay? So this is going to be, again, sine squared x is equal to 1/2 times 1 minus cosine 2x, okay? So keep that in mind. It's a minus. The sine is a minus. The cosine is a plus. So this is going to become 1/2 times 1 minus cosine 2x, okay, dx. Integrate that from 6 to pi. And we're going to distribute the 1/2. This is 1/2 minus 1/2 cosine 2x, okay, from 6 to pi. Oops, I didn't integrate. Well, what am I doing here? I just distributed. Okay, 6 to pi. Okay, so what does this become? This is going to be 1/2 x minus, well, this is going to be a u sub. U is equal to 2x. Du is equal to 2 dx, right? There's my dx. Okay, so this is 1 over 2.
But why did you, sorry, why did we choose u as 2x, not as cosine? Like, what is the principle around it?
Because I can easily integrate cosine. Because the integral of cosine is just sine, right?
Yeah.
Okay.
Think,
Yeah. Okay, so this is du over 2 is equal to dx, right? d over 2. Okay, so this, I'm going to integrate this guy. I'm going to pull this into two different integrals, okay? I'm going to go integral of 6 to pi of 1/2 dx minus the integral of 6 to pi of 1/2 cosine. I'm going to pull the 1/2 out in front. 1/2 cosine 2x, right? dx. Okay. This becomes the integral of 6 to pi of 1/2 dx. Well, I'm going to integrate that actually. Okay, that's just 1/2 x from 6 to pi minus, okay, 1/2 times the integral. I'm just going to put an integral sign there. I know it's a definite integral, but I'm just going to leave it like this for right now. Okay, you'll see why in a second. Okay, this is going to be u. Okay, u. Okay, of, well, I can evaluate the limits. That's fine. That's actually pretty easy. This is going to be 2 pi, and this is going to be 12, right? Just multiply those by 2. Okay, this is going to be cosine of u du. Cosine u du. Okay. Well, what's the integral of cosine? That's sine. So this is 1/2 x evaluated from 6 to pi. Okay, minus, okay, 1/2, okay, okay, minus 1/2 of, what are we doing here? Yeah, okay, 1/2 of, just this is sine, right? This is in the sine u, okay, evaluated from 12 to 2 pi. Okay. Did I do something wrong? Maybe I did something wrong. It turned into 1/2. What are you talking about? Turned into 1/2. What turned into 1/2? The d over 2, right? d over 2 turned into 1/2. Where did the d over 2 go? Oh, where did the d over 2 go? It turned into 1/2. Yes, exactly. Does that make sense, Sierra? It's the 1/2 out in front. Okay, so we have a d over 2, right? And then that's du times 1/2 is d over 2. If you really want, I can do this. Okay, if it makes you feel better. Okay, if it helps you track. Okay. Okay, so now we're just going to plug in and figure out what our values are. Did I already have a 1/2? Let me think. Let me think for a second. Yes, I already had a 1/2. Thank you, Susan, for seeing that. Okay, so this is 1/4 actually. It's 1/2 of 1/2. Thank you very much. I did miss that. Thank you. I did make a mistake here. Okay, yeah, it's 1/4 exactly. So this should be 1/4. Thank you. I went too fast. I apologize. Good catch. Good catch. Okay, very good catch. Okay, so this is 2 pi. So now what I'm going to do, I'm going to plug these in. So this is going to be pi over 2 minus 6 over 2 minus 1/4 times the sine of 2 pi minus 1/4 times the sine of 12. Okay. Okay, well, what's the sine of 2 pi? That's 0, right? Okay, so this becomes pi over 2 minus 6 over 2, which is 3, minus 3, plus 1/4 times the sine of 12. Make sure you know that this is in radians. Okay, it's not degrees. Okay, how do I know it's radians? Because it's in terms of pi. Okay, it's in terms of pi, so I know that's radians. So this is just a number, and you could figure out what that number is if you really wanted to. Okay, does that make sense? Okay, let's talk about tangents and secants. Tangents and secants. Okay, tangents and secants. So we've got some rules for tangents and secants.
Professor, what we didn't get like the half from the beginning outside the integral? Can we do that? Like
Sure.
from the beginning, like why we didn't get like the half outside the integral and we worked it out, and then when when we substituted u, we have to put du in the whole thing. And why we didn't change the integral from, you know what I'm saying?
You can
Like,
pull it
what
out.
I mean is
Are you going to let me speak?
oh, sorry.
Okay. You can pull it out in the beginning if you want. The problem is you're just going to end up having to distribute it later on to get your value.
All right. Got it.
Okay. So so 4. Okay, for the integral of tangent. Okay, the integral of tangent of m. I say m and I write n. Okay, tangent of the mth power of x, secant to the nth power of x dx. Okay. Okay, number 1. We only have 2 rules for this one. Number 1, if secant, okay, is even, factor out, okay, secant squared, factor out a secant squared, and convert remaining secants to tangents. If secant is even, okay, oh, is even, okay, sure. If you want me to rewrite it that way, that's fine. If power of secant is even, comma, let me capitalize it for you too. If the power of secant is even, comma, okay, factor out secant squared, and then, sorry, we need to make sure we're using proper English here. Okay, and then convert the remaining, okay, the remaining tangents into secants. Comma, using secant squared x equals 1 plus tangent squared x. Okay. Okay. Does that make sense? Okay, number 2. If the power of tangent is odd, if the power of tangent,
Excuse me, Professor.
yeah? What's up?
for number 1, is it remaining tangents to secants or secants to tangents?
Convert the remaining secants to tangents.
Okay, because you have it flipped on me.
I have flipped. I'm sorry. You're right. Thank you. Thank you. Okay, yes. I was looking at the next one. Sorry. The remaining secants into tangents. Okay, I got too hung up on making this grammatically correct. Okay, so if the power of secant is even, comma, factor out the secant squared x and then convert the remaining secants into tangents, comma, using secant squared x equals 1 plus tangent squared x. Okay, that's correct. Okay. Okay, number 2. If the power of tangent is odd, factor out a secant x tangent x. Secant x tangent. Basically what we're doing is we're getting our integration factor. We're trying to get our integration factor. Pull it out, factor out an integration factor, and then deal with what's left over. So factor out a secant x tangent x, okay, and convert the remaining tangents to secants. And convert the remaining secants. Okay, am I doing this right? Nope, I did it backwards again. What the frick? Okay, remaining tangents, okay, to secants using, okay, tangent squared x equals 1 minus secant squared x. Okay, it's good. Okay, also note, okay, that the integral of tangent of x is equal to the natural log of the absolute value of secant of x plus c, and the integral of secant x is equal to the natural log of the absolute value of secant x plus tangent x plus c. We already derived these in the previous chapter, okay, using logarithmic integration, differentiation. Okay. Okay, so we need to take special note of that as well. If we're just left with one integral, then we can just directly go. If we're just left with one, the power is 1 for either of these, we can go directly from the integral into the answer. Okay, so if we break off a bunch of them, we're just left with 1. It's like, well, this will be our answer. Okay, number 4. Okay, would it be secant squared x minus 1? Let me think about that for a second. I don't think so. Is it minus 1? Maybe it is minus 1. Let me go back. Let me go to the big book and see why I would have written it backwards. So yeah, it probably is secant squared. Let me look at another problem here. That's secant tangent. It is secant squared minus 1. Yeah, secant. I wrote it backwards. I'm sorry. It is secant squared minus 1. Yes, you were right. Okay, good job. Okay, secant squared x minus 1. Perfect. Awesome. Okay, yes. Make sure we update that in the notes. So secant squared minus 1. Perfect. There we go. Okay, nice. Okay. So let's do a problem. Okay, we want to do the integral of tangent to the 6x secant to the 4th x dx. Okay, so what are we going to do here? Okay, so we have even, right? We have even powers, so we want to factor out a secant squared, right? We have even powers, so we want to factor out a secant squared. So let's do that. So I'm going to get tangent 6x times secant squared x times secant squared x. Okay, why? Because what's the derivative of tangent? What's d dx of tangent of x? Isn't that secant squared? Right? So if I can get everything in terms of tangent, and then we break off a secant squared, that's my integration factor. Okay, that's my du. This is my du here, right? Isn't that my du? If u is tangent, then that's just going to be my du. Does that make sense? Good. Good. Okay. So, and then what are we going to do? We're going to change the secant squared into 1 plus tangent squared, right? So this is tangent to the 6x times 1 plus tangent squared x. Okay, times secant squared x dx. I'm going to distribute. Okay, integrate tangent to the 6x, okay, times secant squared x plus tangent to the 8th x secant squared x. Okay, I'm going to break this up into 2 separate integrals. Dx. Okay. And so now what do we get? We're going to get, this is just going to be u equals tangent of x. What's du? Du is equal to secant squared x dx. Okay. So this just becomes the integral of u to the 6th power. Du. Over here, same thing. This is just the integral of u to the 8th power du. Same u du substitution. Okay, so this becomes 1/7 u to the 7th plus 1/9 u to the 9th plus c. But what was u? U was tangent of x, right? So this is going to be I'll put this in descending order. 1/9 tangent to the 9th of x plus 1/7 tangent to the 7th power of x. Okay, plus c. Okay, and that's the answer. There. Good. Okay, let's move on to number 5 here. So too much fun. Okay. Okay, number 5. Number 5, we want to integrate tangent to the 5th. Okay. Tangent to the 5th, secant to the 7th. Okay, tangent to the 5th, secant to the 7th. Okay, let's try that one. Okay, tangent to the 5th, secant to the 7th of x. Okay. Dx. Okay, these are odd, right? Odd. So what I'm going to do is I'm going to factor out a secant tangent, if that makes sense. Okay, it's an odd power, so I'm going to factor out a secant and a tangent here, and then convert. Okay, convert. I've got an odd power of tangent, so that's what I care about. So I've got an odd power of tangent. And so what I can do is I can factor out a secant tangent here. So I'm going to get tangent to the 4th x, secant to the 6th x of secant x tangent x. Okay, or tangent x, secant x, however you want to think about it. Okay. And now what I'm going to do, I'm going to convert these guys into secants. So this is going to be, okay, secant minus 1, right? Secant squared minus 1. This is secant squared minus 1 squared, because it's tangent squared, times the secant to the 6th of x times secant x tangent x, okay, dx. Okay. I dropped an x there. Okay. Which is always good because, you know, you want to always drop your x's. They're bad news. Okay. Okay. So secant squared x minus 1 squared. Okay. So now I'm going to distribute. Okay. Exactly. Okay. And so distribute this thing out. Okay. Or multiply it all out. Okay. Didn't you just tell me it was secant squared minus 1? Eliel told me it was secant squared minus 1. So take it up with him, Ravi. Okay. I defer to Eliel on this one. Okay. So, no, I got it wrong initially. I got it wrong initially. So it is secant squared minus 1. Okay. No, it's all good. It's all good. Thank you. Thank you. We all make that. You learn more from your mistakes than from your successes. I learned in life. Okay. It's all good. It's good to make mistakes. The thing is, you just don't want to repeat your mistakes. That's the thing. You don't want to be. That's stupidity. So making mistakes, that's great. Repeating mistakes, that's bad. Okay. So this is going to be secant to the 4th x minus 2 secant squared x plus 1 all times secant to the 6th x times my integration factor, which is secant x tangent x dx. Okay. So again, I'm going to distribute here. This is going to be secant to the 10th x minus 2 secant to the 8th x plus secant to the 6th x all times my integration factor of secant x tangent x dx. Okay. So now we're ready to do our u substitution. U is going to equal to secant x. Du is equal to secant x tangent x. Okay. And so this is going to be u to the 10th minus 2 u to the 8th plus u to the 6th du. Oh, that's nice. So now we're going to integrate. This is going to be 1/11th u to the 11th minus 2/9 u to the 9th plus 1/7 u to the 7th plus c. Now let's plug in what our u was. That was just secant. So it's 1/11th secant, okay, secant to the 11th of x, okay, minus 2/9 secant to the 9th of x plus 1/7 secant to the 7th of x plus c. Always plus c. Always okay. Okay. Okay, number 6. Are we having fun yet? This is good stuff, man. This is good. Okay, let's try this one. Number 6. We're going to take the integral of the tangent cubed of x dx. Ooh, spicy. Spicy here. Tangent cubed of x. What do you think we're going to do here? Any ideas? Tangent cubed of x. There are no secants. So I can't break off a secant squared. I also can't break off a secant x tangent x. So the two rules don't really work here, right? They don't really apply. Okay. What? Oh, wait a second. This is odd. This is an odd tangent. So it does work. Okay, so what are we going to do? We're going to break off. Wait. No, we're going to break off. Can we break off a tangent? Can we break off a tangent here? Let's try to break off a tangent. Okay. Sine cosine. Yeah, I don't know about sine cosine. You might be able to do it that way. Yeah, I don't know. I mean, we could try sines cosines. Okay. Yeah, Victor, you got it right. Let's try this. Let's just try this. Let's tangent squared x times dx. Okay, so then what can we change this into? This we could change into secant squared minus 1, right? Can we change that into secant squared minus, that's secant squared x minus 1 times tangent x. We're just playing around. It's good to play around sometimes and see if things are going to work or not work. But lo and behold, this worked. Why? Because I didn't break off a secant squared x, but I was actually able to get a secant squared x with a tangent. So that's kind of cool. I was able to get a secant squared x right here by converting the tangent squared into a secant squared minus 1. So then what does this become? This becomes secant squared x tangent x. Oh, okay. Okay, secant squared x tangent x. Okay, or maybe I'll put the tangent first. Let's put the tangent first, because the tangent is the u, and the secant squared x is the du. Okay, dx minus the integral of tangent x dx. Oh, okay, that's kind of cool. Okay, so what is u? U is equal to tangent x. What's du? Du is equal to secant squared x. Okay. So this one, there is no hard and fast rule. You just got to play around with it. So this is going to be the integral of u, du, that's going to be u squared over 2. Okay, so this is going to be 1/2 tangent squared x minus, but what was the integral of tangent? What did we say the integral of tangent was? Oh yeah, the integral of tangent, that was our natural log of secant x plus c. That's it, done. Number 7. Okay, let's do one last identity. Let's do a proof. You ready for a proof? Let's do a proof. Let's do a proof. It's proof time. Let's do an identity. Let's do a calculus identity. Last problem of the day. We're going to do an identity. Okay. It's really not an identity. It's just a calculation using some stuff, but it's tricky. It's tricky. So we're going to call it an identity. It's just a problem. We're going to get from solution to save state, and we're going to create an identity. So it's a proof. Okay, we're going to go from a start to a finish. Okay, we want to find out what's the integral of secant x dx. What's the integral of secant x dx? Things that make you go, Well, what's the derivative of secant? What's the derivative of secant? Any ideas? Okay, the derivative of secant x is what? Okay, it's secant x tangent x. Thank you, Martin. Okay, this is secant x tangent x. So that doesn't really work, right? Because, man, I would need a tangent x as my du. Okay. What if we tried integration by parts? Would that work? Could we do integration by parts here? Let's look at Lie8 real quick. Lie8. This may not work. It may or may not work. We'll see. Okay. Integration by parts. Will integration by parts work here? Okay. Lie8. So what is 1? 1 is algebraic, right? That's 1. 1 is algebraic. And what's secant? Isn't that trigonometric? Isn't that trig? Okay, so this is trig. Right, so that's secant. Okay. Okay. Yeah, secant is 1 over cosine. Okay, yes, got that. Okay, so we would want to do the algebraic before the trigonometric. So u is equal to 1, du is equal to 0. Okay. dv is equal to secant x, and v is equal to, yeah, that doesn't help me much, does it? Because aren't we basically asking to do the same problem that we just did? And that doesn't help us. Does that make sense? Why this doesn't help us? Because we're basically asking, do we just make the algebraic 1, then the v to u goes to 0, and the udv, the integral of udv is just the original function. Right? We didn't make any progress whatsoever. So integration by parts is out. Oh, that sucks. Okay, so we're gonna have to get really tricky with this one. Okay. Change to inverse cosine. Then the cosine is odd. What are you saying? Change to inverse cosine, then the cosine is odd. 1 over cosine? Then the cosine is odd? It's not squared. LEL says it's not squared. Okay. Yeah, we can't, I don't know. I mean, he's saying change it to 1 over cosine. Okay, so 1 over cosine of x is secant integral, right? Dx. Okay, so how do we do that one? That would have to be like a
U sub.
u sub.
We can like, yeah.
Okay, let's do a u sub on cosine x.
Like,
Du is equal to negative sine x dx. The problem is I don't have my du. Does that make sense? Oh, but then you're saying you let u be equal to, let x be equal to inverse cosine of u. Yeah, that's going to get really complicated really fast. Do you see how that's going to get really complicated really fast? Does that make sense? Because if you tried to plug this in, this is going to be 1 over u du over negative sine x, right? Times, but what's x? This would be 1 over u times du over negative sine of the inverse cosine of u. Okay, and did that make it easier or harder?
order.
That made it harder. So this guy's out. Strike 2. Strike 1. Strike 1, u sub. Strike 2 is integration by parts. So you want to see how this is done? Not everybody at once. Not everybody say yes at once. Okay. So yes. Yes, Professor Holman. Yeah. There you go. Exactly. Let's get some air in those lungs. Okay. Yeah. Yeet. 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 Okay. Let's see how this is done. Yeet. Exactly. That's what I do to my son every morning. I yeet him. I yeet him from a bed to the dishes. Like bed to dishes. You got yeeted. Okay. Yeet. Okay. I do play a lot of Minecraft. So I do yeet a lot. Okay. A lot. Okay. Yeah. Okay. So let's see what the trick is on this one. The trick is tricky. Okay. The trick is tricky. It's really an easy proof. But okay, let's prove the identity here. Let's prove the identity. Let's do proof. Proof of an identity that I'm going to derive. Okay, proof. Proof what? Proof that this is equal to something that doesn't involve an integral. Secant x, okay, dx is equal to, and I'm going to have a little magic 1. We're going to have a magic 1 here. You ready? You ready to get on the magic 1 bus? Let's ride the magic 1 bus. Okay. Okay. So we're riding the magic 1 bus. Okay. What's the magic 1, you say? Well, here it is. Here's the magic 1. I get way too excited about this stuff. But it's my life. You know, I've dedicated my life to this stuff, so I should get excited, right? Okay. There's a fine line between genius and insanity. And I ride that line daily. Okay, just letting you know. Okay, secant x times the magic 1. What's the magic 1? The magic 1 is this guy here. This bra here. Okay? What up, magic 1, bra? Okay, this is secant x tangent x over secant x tangent x. And you're like, how did anybody figure this out? Okay, it's people who have absolutely no life and figured this out. Okay, way too much time on their hands, and way too much intelligence, more than I have, figured this out. They're like, oh, dude, this is simple. You just multiply the top and bottom by secant x plus tangent x over secant x plus tangent x, and you're done. I'm like, what? Where did you get that from? Like, years of experience. Years and years of experience. It's the magic one. This is our magic one. We're right in the magic one bus. Magic one. Magic. Okay, so now things just got a lot better for us. You're like, you're insane. How did they get a lot better for us? Well, they did. Just trust me on this. Just go with it, okay? Just go with it. Okay, so let's distribute the top. The top is going to be secant squared x plus secant x tangent x. These both look familiar. Okay, all over secant x plus tangent x. Okay, cool. Okay, all over secant x plus tangent x. Now I'm going to do a u sub on this. Okay, well, what's my u sub? What's the derivative of secant? What's the derivative of secant?
Secant x tan x.
Yeah, it's this guy here. What's the derivative of tangent? What's the derivative of tangent? Come on, Fady, don't fail me here.
Secant squared.
Yeah, secant squared. So the derivative of this guy is right there, and the derivative of this guy is right there. Oh, sweet. So we've got u equaling the denominator here, secant x plus tangent x, du, what's du? Du is equal to secant x tangent x plus secant squared x. Nice, dx. Okay. There's a dx here. So what does this become? Well, lo and behold, the entire numerator is my du, and my entire denominator is my u. So this just becomes the integral of 1 over u du. That is some spicy math. Spice it up. Okay, spice it up, spice it up, spice it up, spice it up. My son, when he was in 2nd grade, he would come home and he'd be like, spice it up, Dad. Spice it up. Spice it up. I'm like, what is wrong with you, child? And he's like, you got to spice it up. I'm like, spice what up? And he's like, you got to spice up your sentences. She says, that's what my 2nd grade teacher tells me. He said, you got to spice it up. You don't say the cat sat on the mat. That's not a spicy sentence. You got to spice it up. I'm like, okay, I'll do that in my math class. I'm going to spice things up. We're going to keep it spicy. Okay? So I don't ever try to say, oh, this problem is harder. No, that has a negative connotation. It'd be like saying no parking. That has a negative connotation. Instead, you should say park elsewhere. That makes people feel nice about themselves. You're just telling them to park elsewhere, not no parking. No parking comes off as, forceful. So I'm not going to say that this problem is harder. We're going to call this problem spicier from now on in this class. These are going to be spicier problems, okay? They're just a little spicier. Okay? Exactly. Just a little spicier. Okay, so the integral of 1 over u, what's the integral of 1 over u? You guys are on it.
The absolute value of u.
Yeah, natural log absolute value of u plus c. But what was our u? It was secant
x plus tangent
plus tangent x. Tangent x, okay, plus c is equal to the integral of secant x. Boom, look at that. There's our identity. QED, quid erat demonstratum. It has been demonstrated. It has been proven. And I am done for today. Okay, come back for trig substitution and partial fraction decomposition tomorrow. Try not to let your head explode. Okay. Woohoo. Okay, I'll see you guys later. Enjoy your evening. Make sure you do your homework.
Thank you, Professor.
Yeah. Bye.
Professor?
Yes? Question? Hi.
Hi, I had a quick question
Sure.
about my test.
Yeah.
I was wondering, I was wondering if you got it. I sent you an email. I had
Yes.
some problems near the end about converting it to a PDF.
Yes. I believe I received. I can check right now.
Okay.
You should have a grade in Canvas.
And I can check.
Okay.
Also, for one of the questions, there's a misinput, and I got marked off.
Okay. Which question was that?
It was number 2. I even included it in the work.
Oh, okay. Okay. I'll just give you credit for that one then.
All right. Thank you so much.
Sure. Absolutely.
Have a good day.
Okay.
And sorry, I had another quick question.
Yeah.
The test that we took yesterday was probably one of the lowest I've ever scored on a test.
Oh,
And I was wondering if there are any I was wondering if there are any things that you'd recommend doing before the test. I did all the homework. I did everything.
I would
in the
honestly, I
classes.
would make sure that you have every single example that we do in class memorized.
All right.
Does that make sense?
Yeah.
Okay.
All right. Thank you.
Yeah, you're welcome.
Have a good. All right. Bye.
Bye.